From this year, we received again grant from DBT for 4 subjects: statistics, mathematics, electronics and physics. And I think this is the first session, or this is the first lecture on, on which or for which you are present in this webinar. So really this is a feast to our faculty members, to our students. One more thing I want to mention, that our college established in 1970. Last year only we completed our golden jubilee year. And at present in our college there are 27 PG departments and 12 research centers. Every year more than 100 research papers published in reputed journals. We have DBT Stars College Scheme, we have DST Fee Scheme, we have also CPE Scheme, College with Potential Excellence by UGC. And one more important thing that I want to mention, that in last accreditation our college received A++ grade with CGPA 7.9. So this is our march in last 50 years. Like we started in 1970, and after 50 years we reached up to this stage. And one of the important behind it, that we get a very good students, we get a very quality students. And due to our alumni, due to our students, our college is at this stage. And definitely future will march in a different way. In first 20 years we set up our college up to the graduate level. In next 20 years we set up our college up to postgraduate level, and now we are interested to move towards the research. So at this stage 12 departments are having research centers, and in future we want to increase those research centers, so that postgraduate teaching and research will work in hand. One more important thing that I want to mention, that from next academic year we are going to adopt autonomy. So that is a next step of our march, and definitely for that purpose we are going to discuss with the various experts through these webinars. Definitely we will get very good faculty members on our board of studies, on our faculty, on governing council. And if we get a faculty from all corners of a country or from the outside the country, and definitely will implement the autonomy effectively. Madam, whenever we require some help from you for the subject autonomy, for the subject statistics, for autonomy, I request you that you give your valuable time to our statistics department, to our professor. With these words, again I declare that this webinar is inaugurated, and without wasting more time, better to move towards the Asha Kamath madam, so that his expertise will be helpful to us. His expertise will be helpful to our students as well as to our faculty. Thank you, madam.
Thank you. Thank you, sir. Within 2 minutes, I will just introduce Dr. Asha Kamath madam. She is basically from Karnataka. She completed her statistics education from Bangalore University, and since 1990, she has delivering many lectures in the medical institutes in Manipal. Presently, she is the associate director in Prasnna School of Public Health, and in the same, she is professor and head Department of Data Science, which was earlier named as Department of Statistics. So recently, she is elected as a member for International Statistical Institute for 2 years, 2019 to 2021. She has more than 200 research papers on her credit, and she has co-investigated 14 research-funded projects. So her biodata is very rich. Her specialization also is unique in public health and epidemiology. So looking into pandemic situation, deliver a lecture on public health, use of statistics in public health and epidemiology. I am very much thankful to her for accepting my invitation. So, madam, I request you to start with your session. I have already allowed you to present your PPT also.
Am I audible?
Yes, madam. Yes.
Yeah. So thank you, Professor Kasturi and the team which is organizing this event for thinking of inviting me for this particular talk. So, let me just share my screen. Is my screen visible?
Yes, yes, ma'am. Yes. Is it visible?
Yeah. Okay. Okay. Good afternoon to everybody. I guess major chunk of the audience for this is the student population. Am I right?
Most of the student populations.
Yeah. And they're students of masters in statistics or other courses too?
Many are undergraduate students, and few are
Okay.
postgraduate also.
Okay. So I was asked to give a talk on statistics in public health and epidemiology. So what I have planned is I'll briefly give an introduction to epidemiology and public health so that with this introduction, I think the students of statistics should be able to understand what is the role of statistics in these two areas. And then I'll just take you through some of the applications of statistics in these two areas. So let me just introduce to you what is epidemiology and public health. So if you look at definitions, health, disease, illness, sickness, these are some terms which are commonly used in public health as well as in epidemiology. And as per the World Health Organization, the definition of health stands for complete physical, mental, social well-being, not merely the absence of disease or infirmity. And if you talk of disease, it refers to either a physiological dysfunction or a psychological dysfunction. And illness is a very subjective state of not being well. And if you talk of sickness, it's a state of social dysfunction. So when you say somebody is sick, the person need not be ill. It's only a feeling that you don't want to be in a social gathering. And if you look at the public health, it's a science and art of preventing disease, prolonging life, promoting health and efficiency through organized community effort. So if you look at actually the concept of public health, it is more towards well-being of a population or the public or mass. So what is this public health? Science and art of protecting and improving the health of communities through education, promotion of healthy lifestyles, and research for disease and injury prevention. So this is what was adopted by the Association of School of Public Health in 2010 as the definition for public health. And if you look at statistics, it's a collection, science which deals with development and application of most appropriate methods for collection of data, presentation of collected data, analysis and interpretation of the results, making decisions on the basis of such analysis. So you can see that whenever we deal with epidemiology or public health, there is collation of a mass of data. So we have to apply these statistical tools to make sense of the data and have certain policies either amended or implemented for betterment of the well-being and health of the population. If you look at epidemiology, it is defined as the study of frequency, distribution, and determinants of health and other health related conditions in a human population. So basically, what are you trying to do is application of this study to prevention of disease and promotion of health. That is what is the definition of epidemiology. So Systematic collection, analysis, and interpretation of data is what is involved in most of the epidemiological studies. So epidemiology is a science. So when you talk of frequency in epidemiology, it's basically number of times an event of interest occurs. It could be number of times a disease occurs, number of times a disability occurs. So basically, you are answering the question of how many are involved in that particular event, be it a disease or a disability. So it's a quantitative science because whatever is being observed, you're trying to quantify it and give a numerical fact corresponding to that entity which is being observed. If you look at the distribution in the epidemiology, distribution of an event can be looked at by person. Is the disease varying by age? You talk of people with hypertension, which is nothing but high blood pressure. So, as age increases, the blood pressure increases. So, you'll find more of aged people being shown to be hypertensive. Does it change by place? So if you look at people living in high altitudes, are they likely to be more hypertensive than people in the plains? So that is something geographical location. Is it, or is obesity more common in the Western population than the Asian population? So you can have observations of these kind of patterns across geographical region. And then of course with the time, how do events change with time? So you look at, say, respiratory diseases, that means cold, fever, etc. It is more common during the rainy season, a little lesser common during winter season, but in summer you wouldn't find occurrence of cold and fever to that extent. So, the events which are being observed are going to change by person, characteristics of the person, uh, by the locality in which the person is residing, and over the period of time, over year. Maybe seasonality is there. Certain diseases occur only in seasons. Really, maybe in the summer season, you'll find more of diarrheal diseases coming because water scarcity is there. There could be contaminants in the water and people end up with diarrheal diseases. So epidemiology studies distribution of diseases, answers questions like who, person, so who, place, where, and time, when. So you're trying to describe these health events by answering these three questions. And if you look at determinants, people living in the same area, like for example, now we have COVID, right? So why is it that everybody is not getting infected by COVID? There are only a few chunk of the population in any given region that is getting infected. So you want to know what are the factors which are responsible for presence or absence of the particular event of interest. So epidemiology studies what determines health events. So it tries to answer the questions like how did it occur in these? That means how did they get the disease? Did they have contact with person who already got infected? And what was their movement in a given locality? So where did they try to contact this from? And the next question is, this person is not alone. There were many others who were there. Why did only he get? So you're trying to find answers to these things. So let's move on and see for each of these components, what are the statistical tools we would be applying. Then when I talk of diseases and other health related events, let me tell you again, epidemiology focuses not on diseases alone. It's not always patients. It's also related to health related events. It could also be people who are physically active. So I want to study what proportion of people in a given population or a community are physically active. That means they are regularly going for their exercise, maybe half an hour of walk and some, brisk exercises that they do. So I would also look at that. So it's a broader science in that sense. And then it deals with basically human population. So diagnosis and epidemiology diagnosis and treat communities and populations. It's not just looking at an individual like what is done in the hospitals. In the hospitals, you look at a single patient with a particular diagnosis and treatment is given for that. Whereas in epidemiology or public health, you look at a community, you look at a population, and then you try to diagnose that population and see what is the intervention that you are trying to provide to this community so that you can bring down the level of the disease or better the quality of living of people in that particular community. So epidemiology is a basic science of public health. So public health major component is epidemiology. Epidemiological studies have direct and practical applications for both prevention of disease and promotion of health. So it is a science as well as you have a practice applied in. So you can, in other words, say epidemiology is an applied science. Let me just take you through some landmarks in the history of epidemiology. So first of history is documented is by Hippocrates in 460 BC, where he tried to relate environment and human behaviors, how it affects the health. So the place of stay and the behavior, how a human interacts with its fellow beings, how it affects the health, how would people fall sick. So that is documented by Hippocrates. If you go further down the timeline, the first of the applications of statistics came in by John Grant, who studied the mortality bills, which is documented in churches, and he quantified the births, deaths, looking at the cause of death, and identified that some of the diseases lead to mortality more often than others. So that is where the first application of statistics came in, which laid the foundation for epidemiology. Then in 1947, a crew which was traveling in a ship was found to be having certain symptoms, and that was identified as scurvy by Lind, which he found that when they were given citrus fruit, which was available in the crew, helped them to recover faster, which was nothing but a disease of vitamin C deficiency. So this was again by Lind. He documenting about who were the people who had problems. And then when he gave them citrus fruits, he found that the people who ate citrus fruits in the ship were able to recover faster. Then William Farr, he established application of vital statistics for evaluation of health problems. So all those rates of birth, death, and disease rates were taken in to assess what is the problem of health which is existing in a given population. And all of us have heard about cholera, and the source of cholera infection was identified by this man John Snow, where he found that there was this particular epidemic happening in London. So when he spotted them in a map. He identified that it was the pump which was supplying water. People who were taking that water were the ones who were infected. So what he did was he broke the handle of that water pump, and when people stopped drinking that water, the cases of cholera started coming down. So this is something where John Snow applied some statistical tools, which we will see some examples. And similarly, in 1872, Alexander Lewis systematized application of numerical thinking by giving quantitative reasoning to applying some of these to the existing health problems. Then Bradford Hill, he suggested criteria for establishing causation. So cause and effect. So, if you do not take vitamin B adequately, you are going to get vitamin B deficiency, beriberi. So these kind of cause and effect studies were performed by Bradford Hill and his team. So epidemiological thought actually emerged as early as 460 BC, and it flourished into a discipline only in 1940s after the concerted efforts of all these people whom I have put across in the landmark. So originally it was considered to be investigation and management of epidemics, Lately, it extended to endemics, even communicable and non-communicable diseases, where studied in terms of the techniques used for studying epidemics. And of late, it's applied to all diseases and even to studies being done among hospital patients. And that has come out as a branch called the clinical epidemiology. So as you all know, purpose of epidemiology is prevention of disease and promotion. So when you're trying to study a disease, you should know how is the disease occurring. So you should know what is the natural history of the disease. Then you need to describe the health status, who, where, when get it. Then you need to establish what determines the disease. Why is it only some in a particular age group get and not others? Are males having more of the disease than females? So you're trying to find out such determinants. And then you need to evaluate and see what is the effect of interventions that you are planning for these kind of diseases. So we can divide it majorly into descriptive epidemiology and analytical epidemiology. Descriptive, when I say, I'm just describing what is the frequency, what is the distribution. So you're answering the 4 questions: how many, who, where, and when. And when you talk of analytical, you're trying to see the determinants. How and why is the question you are trying to answer. So there are 6 major questions, like in any research that epidemiology tries to answer. How many, who, where, when, how, and why. So basic assumptions which go when you are carrying out any study in epidemiology, which also happens to be a major heart of the public health, is that events or human diseases do not occur at random. It is not by chance. There is definitely some causative factor, and there are preventive factors which, if followed, a person can avoid getting the disease. So you basically conduct studies on human populations, look for patterns in the people, establish a cause and effect relationship without even knowing what is the biological mechanism, and you can cover a various wide range of conditions, and it is still advancing science. So how do you measure the disease occurrence? And this is where statistics comes into play. So you are actually measuring it by the frequency or the magnitude or amount of disease in a population. You talk of any disease, say you talk of cholesterol. In any given population, what number of people are likely to be having high cholesterol or high blood pressure? This is what we are trying to quantify. So we are measuring it in terms of frequency or what is the magnitude or burden of this particular disease. So you have numbers which can be used to quantitatively describe, or as a ratio, as a proportion, or a rate. So what do you mean when I say numbers? I'm just reporting 100 people, 1,000 people. Now, when I want to make a comparison, so I say in a town A, there are 100 people with, say, high cholesterol. And in town B, there are 1,000 people with 1,000, high cholesterol. Can I say that town B has got higher people with the high cholesterol? It is meaningless to compare these mere numbers because I do not know. I've got this 100 out of what population and 1,000 out of what population. So the denominator for this is very important if I have to make a comparison, because it might be 100 out of 1,000, which is amounting to 10%. And here it is 1,000 out of a 10,000, which is again 10%. So if you look at comparison wise, there is no difference because the rate is the same, right? So this is what we have to take a call. When are we going to look at the numbers? When are we going to look at the proportions or rates? And when are we going to look at the ratio? So these are the 4 ways that you can quantify and put across the disease magnitude. So as in here, I'm giving you use actual number of events. So 100 cases of TB in a community A. Now you can quantify the magnitude of one occurrence X in relation to another and say the ratio. So ratio of TB in community A to community B is 1:10. So if you have 1 case there, you see 10 cases in another community B. 1:10 is the ratio. Now this gives you an idea about how much more load of the disease is there in a given population. Other way could be, as I told earlier, convert it to percentage and put it as a proportion, or you can define it as per whatever population, per 1,000 population, per lakh population, as shown here for measles cases in US population under 5. So as I said, you cannot compare merely based on the numbers. So you have to look at what is the denominator which has given us these numbers for comparison purpose. So when we call a measure a ratio, we mean it is non-proportional ratio. And when we say it's a proportion, the numerator is a part of the denominator. And when you multiply this by a fixed constant, like say 100, 1,000, 10,000, we get a rate. And this is usually observed over a period of time. So rates can be put in as crude rates, specific rates, and standardized rates. When I say crude rates, you're applying it to the total population of that given geographical area. When I say specific rates, I'm dividing that population into specific groups, like in say age groups. So I can divide that entire population into 10-year age groups and say 0 to 10, 10 to 50, 20, 20 to 30, where I'm taking, mutually exclusive class intervals. So then I have specific rates. So for each age group, I can give what is the rate of occurrence of the disease. Or I can look at it gender-wise, male to female. Is there a difference in occurrence of the disease? Say like, for example, if I talk of breast cancer, definitely the rate of breast cancer is higher for females, and that for males is very, very less. So I can say that females are having preponderance with regard to the breast cancer rate. Then you have standardized rates, wherein you have a common age structure and you're standardizing the rates of both the population that you want to compare to this common age structure. So there are different methods of direct and indirect standardization. I wouldn't go into the details of that. So when it comes to these morbidity rates, if you actually look at it, it's nothing but application of probability. What is the definition of probability for an event? You have favorable number of events to the total number of events. So this is how you're reporting your morbidity rates. And then you multiply it with a constant to convert it to rate as per 100, per 1,000, or per lakh, depending on how small this particular rate is. So two common morbidity rates which are used are the incidence rates. So here we generally have a time period within which you are looking for occurrence of those cases. They are not pre-existing. They occur in a defined time period. So then we call it as the incidence rate. And the other one is the prevalence, where at any given time point or within a defined period, you're looking for all the existing cases, which includes both the pre-existing as well as the newly diagnosed within your period of time or at a given point of time. So that is prevalence. So you can calculate it for different diseases, right? You can look at what is the risk using this by getting a probability of that individual developing the disease. You can also see over time how rapidly is it increasing. So that is what was happening when we were looking at the COVID. Initially, we had few cases, and then you can see that suddenly there was a surge in the cases. So now we are reaching a peak, and then slowly we are seeing that there is a decline in the cases. So after some time, there may be a resurgence of the cases because the lockdown helped us to control this disease. So there was a flattening, but then again, once the lockdown started unlocking, you can see that there are increases in the case. Then we have something called as cumulative incidence. Just like we take cumulative frequencies, you are accumulating. So you are adding up all cases that have been seen during a specified period, and then you divide it by the population which is at risk in that same period. So that gives us the cumulative incidence, where you make in here the use of cumulative frequencies up to a given period of time. So practical challenges are identification of population at risk. So you do not know who are the people who are at risk. So you assume that it is the population of a given locality. and you are calculating. So you assume that the entire population is at risk. They are likely to get this disease. Whereas that may not be the scenario. There may be a subpopulation within this which has got a lesser risk because they are not getting exposed to the particular virus which is causing the disease. So then the projection that we are giving could be underestimation or overestimation depending on whether the population that we are taking has got higher susceptibility or lower susceptibility. Moreover, population is not static. You have people migrating, even if you take a geographical region, or because of birth, population is growing and it is depleting because of the death. So there is a change, which is constant change, which is happening in the population. So that cannot be captured on a real time. So there could be over or underestimation of the incidence rate. So one of the ways is you just take the total population as your denominator. Or other one could be take the person time. What does this mean? You have a group of people that you are observing. So each one is giving you some period. So if the person migrates or dies, say your period of follow-up is 1 year, the person died after 6 months of follow-up. The time contributed by that person to you is 6 months. There's another person who migrated after 8 months. So 8 months of that person's time came to you. And you had two other people who were there with you for 1 year. So total time which all these four have contributed would be 6 plus 8 plus 12 plus 12, which makes it 24 plus 8, 32 plus 6 is 38. So 38 months were contributed by 4 people. That becomes your denominator, and the numerator will be number of people who got the disease. Suppose 1 out of this got a disease, then it becomes 1 out of 38 becomes your incidence density. Similarly, the prevalence rates. So these are some of the rates, common mortality rates which are reported for a population in public health, right? So this is the formula. So if you look at each of these entities in the second column here, you will find that this is nothing but the concept of probability. Numerator is a part of the denominator, right? Out of the whole, what number? So total number of cases, total your sample space, and numerator is your number favorable to the event of interest. Next concept which uses probability is also the sampling. In sampling, for selecting each individual, we have assigning of probability. So if you go for simple random sampling, you are giving equal probability to all. If you go for stratified random sampling, depending on the stratum size, the probability of selection of individuals in each stratum will be proportional to their stratum size. So some of the big budget nation representative studies commonly done at a national scale, the large surveys, are the regular rounds of survey done by the NSSO, the National Statistical Service Office. They conduct once in every 2 years surveys with regard to birth, death, certain mortalities and all that. So here they are using stratified random sampling, where stratification is done on the basis of the states of India. From each state of India, they're picking up samples. The next study which is carried out is the economic study, which is carried out with the National Center for Economic Research, where again they use the stratified random sampling. Here you're looking at the expenditure and consumption surveys. So you're carrying out studies of this kind for families which are selected from each of the states, because it's to give a representation of India. Then you have here the proportionate probability proportionate to size sampling, which is used for IRS surveys. Similarly, you have regular market surveys. These are smaller surveys. So here it's basically the non-random sampling, which is judgmental and quota sampling by target groups. Because when you do a market research survey, it has to be people who are going to buy those commodities. So you cannot have a list of the people who are going in to buy these commodities beforehand. So usually this is done by going in for a convenient sample or a judgmental sample. Similarly, the post-survey corrections are done by weighting 1 or 2 variables to give universal estimate from the IRS survey. And then in public health, we do a lot of school health surveys to identify what are the uh, risk factors for these children as they grow, or what are their health problems as they are doing their schooling. And this time we go in for the cluster sampling. So, schools are basically of three cadres: the government school, the aided schools, and the non-aided schools. So we want to have representation from all of this. Then we do a stratification there and make sure that we have schools from each of these. And under each of these stratum, we are going to select a few schools which are representative. That is when we go in for a cluster sampling. And if you look at the immunization coverage, which is done for the children, this is again using the cluster sampling. So in a given geographical region, you are selecting 30 wards, and you are selecting 7 children from each of the 30 wards. So a total of 210 children are taken from a given administrative unit of a district. So this is how you are going on selecting your samples for the immunization coverage. Even for certain national health program evaluations, we go in for the cluster sampling. Then we have used the concepts of, we study the concept of percentiles. What are percentiles? These are values which divide your data into 100 equal parts. So if you take, say, for example, the 60th percentile, what does it mean? 60% of the people are having values below that 60th percentile, and the rest 40% are above it, right? So percentile charts are frequently used in growth monitoring. So when a child is born, the child will have a certain height or a certain weight, that is at 0 here. And as child advances in age, in months, the height or weight of the child increases, but it is not a linear increase. So what we normally do is, for any given age, you get the percentile values, and then you put up the percentile lines. So you can see here there are 3 percentiles which are depicted: the 90th percentile, the 75th percentile, 50th percentile. You'll have some more charts which also give you here at the bottom the 10th percentile. So if I find a child which is below 10th percentile, what does it mean? It means that child is not having adequate growth. The child is malnourished. So then there has to be some intervention provided to this child, because if the intervention, if supplemental feeding is not given to this child, child is not going to catch up with its growth. If the child's weight falls between the 10th percentile to the 25th percentile, probably it is just few dietary modifications which will help the child to catch up with its growth, right? And if it is anywhere between the rest of the band, it is in a normal growth pattern. So we need not really worry much. So the worry starts if it is below the 25th percentile, and if it's below the 10th percentile, the possibility that child will need a treatment. It has to be admitted in the hospital, and probably, the food which it is eating is not able to be digested. The metabolism is weak, so some drugs will have to be administered to this child to make the digestive process better. So this is what I was talking about a little while ago regarding the COVID. So we see a peak, and then social distancing is what has been advocated. So with this, you'll have a decline in the cases. So gradually it will decline. We have not yet reached this phase, right? We are yet to reach this phase. We are still somewhere here only now. So with the time, we will reach here. But then you can always expect that there will be a resurgence of the cases, because unlock has not completely happened. So you could have a rise in case coming, and there will be a second peak that you see. And what is this curve? It's our very popular normal distribution curve, right? So this is depiction of the mortality rate over time, where you use a line graph. And this was because of measles, right? The death because of measles. So you can see there are 3 categories. One was under 5, one was an infant, which is 0 to 5, and the other one was aged 1 to 4 years, right? The yellow line is the infant 0 to 1 year, green line is 1 to 4, and the red is a cumulative of these two. And in 1985, the measles vaccination started. So after which you can see that there was a drop in the death due to measles. So this is how we assess in public health how intervention of vaccination has helped in decreasing the number of cases, right? So this is what I was talking a little while ago. This is the map which John Snow made, right? We call this in statistics as cartogram, right? So you are just identifying each case in the map. And this golden square that you see, this is where the hand pump was, and this was supplying water to all these areas. And you can see that clustering of cases were seen only in those areas which was being supplied by water from this pump. So what did John Snow do? He broke the handle of the pump so that nobody could draw water from that particular pump, and automatically the cases declined. And this is again defining categories of anemia. All of us know that anemia is result of lowering of the hemoglobin in the blood. So there are classifications given. How was this classification arrived? This is again based on the normal distribution. You have the property of normal distribution that if you take 2 standard deviations around the mean, you're going to have 95% of the population. So that 95% is what is defined as the reference range. So many of us go for blood tests, right? So you see in the blood test report, they give the normal range. This is derived from the property of the normal curve. What is this? This is the 2SD limits around the mean. So they have done this study in healthy individuals, collected in a large number of people, this particular biochemical and physiological markers, and given us the range as the normal range. Anybody having values outside of this is likely to have some or the other disease. That is when the doctor takes a call of how to give the treatment. So this is the popular normal curve, which has mean, median, mode coinciding. And this is what I was telling. 1 standard deviation covering 68% of the observed data, 2 standard deviation covering roughly 95%, and 3 standard deviation covering almost all the data, 99.7%. So you will find in some of the studies, there is the Z-score, which is standardization. You have each value subtracting the mean and dividing by the standard deviation, you get the Z-score. So there is a standardization of the values done. Some of them, especially in psychological studies, convert them to T-scores. Some of them convert to percentiles. And then IQ is one such example wherein you are converting them into percentiles, and you are dividing them into, below average, average, good, and Mensa. Mensa are the ones which are highly intelligent. So this is regarding classification of high blood pressure or hypertension, what is called. Same property of normal distribution, but you are looking at the right side of the normal curve. When it comes to malnutrition, you look at the left side of the normal curve. So if it is between 1 standard deviation and 2 standard deviation above the mean, this is mild hypertension. The management of these cases will be done merely by advising for diet control, restriction of salt and fatty foods, and advice for physical exercise. These two will help to manage. The moment it moves above the 2 standard deviation and is between the 3 standard deviation, they need some medication. So some tablets are provided. But if it goes beyond the 3 standard deviation, then they require hospitalization. So the management of the cases also is decided based on these limits. The same way I was talking about malnutrition in that growth chart, the same way it is taken in. Another thing which is generally where you see the application of probability as well as the normal distribution curve is the test used to detect a disease, right? All of us go and get our blood tested for maybe looking for whether any infection is there in us, or are we having high cholesterol, or is the hemoglobin level okay, or is the lipid profile different. So when we identify these kind of tests which give us a continuous reading to detect where to draw the line to say anybody whose value is above this or below this is likely to have a disease, is where we make use of this receiver operating characteristic curve, right? This receiver operating characteristic curve was started from the radars, which were trying to detect the enemy ships and submarines to shoot at them. And many a times they'll miss and shoot their own ships. So there are something called as false positive and false negative. So detecting our own ship as an enemy ship becomes a false positive, and detecting enemy ship as our own becomes a false negative, right? So this graph plots the true positives against the false positive, right? So this plot is what it is. And this line, which is the line connecting the two corners, this is the worst case scenario where even if you toss a coin, you can make a classification that this person has a disease and does not have a disease. So any marker which gives us highest area under the curve is supposed to be the best marker, and we try to look for a point on this curve which is closest to this, because ideally your test should detect 100% of those having the disease and 100% of those not having the disease. So this is one such application. So basic assumption there is you have two normal curves which are overlapping, and you have to draw a line to discriminate between the people who have the disease and who do not have the disease. Another application is the confidence interval. Most of us study that when we have a single sample, if our sample is not a representative sample, we might be wrong in providing an estimate through the mean or proportion. So what we normally do is, along with that estimate, we provide an interval estimate and say that the population value of whatever mean or the prevalence is in this interval, and we are saying that we are confident with 95% that the population characteristics lies in this interval. So we can provide that for each of the variables. So this was a study which was trying to see what were the socio-demographic factors which were associated with leisure time activity. As I told you, you're looking for wellness in public health. So how many of them are involved in any physical activity? So you want to see what is the characteristics of those people who are involved in physical activity. So each of these characteristics was looked at. And since they were looking at a ratio, right? So a ratio, the reference point is 1, right? So if in this interval a 1 is included, that factor is not significant. If it is either to the left of 1 or the right of 1, there is a significant association of those factors to getting involved in leisure time activity. So you can see here the gender is having a significant association. Age group, men and women, there is a significant association, and there is a difference also because there is no overlap here, right? If you look at employment, women employment, no, it is not, because it's crossing the line of 1. So you can make use of these kind of diagrammatic visualization to identify whether there is a statistically significant association of these factors to our outcome of interest. This is another plot, forest plot. This is normally used when we have multiple studies which are done on the same objectives. We are trying to pool the results from each of the studies. So what you see here there are about 9 different studies, and each of them have given the proportion or prevalence of that particular outcome. And then you're trying to pool all of this and generate an overall estimate. So this is what we call as meta-analysis, which you are analyzing the results of all the studies which are done in the past, which is answering the same question. Then moving on to measures of association, and this is when we go in for application of tests of significance. So usually in epidemiology, we have a 2x2 table resulting. So we have people who have disease and no disease. And then we are looking at certain factors which are present in them and which are not present in them. So we get this 2 by 2 table. And whenever we have this kind of 2 by 2 tables or any contingency table of this kind, our favorite test that we use is the chi-square test. So we apply a chi-square test on this and see is there an association of this exposure to the disease. You can also put this in terms of the probability. What is the probability that people with the disease had an exposure? So how many people had the disease here? A plus C. How many had an exposure? A. So probability of exposure among diseased people is A upon A plus C. Similarly, probability of exposure among non-diseased people is B upon B plus D. So we can compute such probabilities. Another way of looking at the same thing could be looking at the odds. What is the odds of an exposure for a person with the disease, for a group with the disease? So odds means what? The event to non-event. So exposure among the disease is A, no exposure among the disease is C. So odds of an exposure for a disease is A upon C. Similarly, odds among no disease is B upon D. Now, if this exposure is causing the disease, what should happen? The odds that you get for the disease group should be higher than the odds that you get for the non-disease group. So you take a ratio of these two odds, and that is what we get in as the odds ratios. Similarly, relative risk. So we have certain criteria. If you have the relative risk between 1.2 and 1.4, we say it's a weak association. If it is between 1.5 and 2.9, we say it's a moderate association. And if it is greater than or equal to 3, we say it's a high association. So you can quantify and give the strength of association depending on the magnitude of these ratios that we compute. Right? Odds ratios, as I told you. So you can look at whether but what you have to take care is that your controls or, the two groups which you're comparing should be representative of the general population. Because if representation is not there, the association that you claim is going to be difficult. And generally we use the odds ratios for studies of rare diseases. Whenever there are rare diseases, you cannot go for large samples. So you take all those diseases and choose a comparable group without the disease to make the comparison of the different factors. Then we use entities called attributable risk. What does this attributable risk tell us? How much risk is more in those exposed as compared to the non-exposed? It's merely a difference in the incidence in the exposed from that of the non-exposed. So if the cases are more among those who have gotten exposure than those, that means there is an increased risk that you are having. How do I interpret it? If I get an attributable risk of 10, what does it mean? 10 of the exposed cases are attributable to the exposure. So what does it mean? If you remove the exposure, 10 cases can be prevented. That is what it means. If you remove, that means if you have some mechanism of stopping that exposure for a population, you can stop 10 cases of that particular disease. That is how we interpret the attributable risk. The same thing can be converted to percentages by dividing the denominator to risk in the non-exposed group. The difference is divided by the non-exposed group risk. What does this tell? If I get this to be 10%, what does it mean? 10% of the disease is attributed to that particular exposure. So if you eliminate that exposure, 10% of the cases can be brought down. This is what you interpret. This is how you interpret the attributable risk percent. Now, when it comes to public health, we are interested in looking at the population attributable risk, because I have to justify why am I giving this vaccination? Why am I putting this program in place? Because it is cost effective. That has to be shown. So we calculate the population attributable risk by taking the attributable risk and multiplying it to the prevalence rate of the exposure. Like, for example, smoking is associated to lung cancer. So if I bring in a smoking control or tobacco control program into place, I have to show that it is cost effective because it's going to bring down the cases of cancer, thereby reducing the cost. So we look at the calculation of the population attributable risk. So if I have a relative risk of 1, my attributable risk is going to be 0 because the numerator is giving me a difference of 0. If I get relative risk greater than 1, attributable risk is going to be greater than 0, which says there is a positive association. If I get a relative risk of less than 1, that means in decimals between 0 and 1, my attributable risk is also going to be negative. So there is a negative association. Moving on to the functions of public health, basically it is assessment of the health conditions and extent measure, and depending on whatever is the magnitude or burden of the problem, you have to implement certain policies, certain legislations to control that particular disease, right? So certain regulations have to be set. And then you have to monitor and see how much of an impact of this policy which has been implemented is seen in bringing down the particular disease or condition. So this is the broad framework for health. You start from here, the governmental health, public health infrastructure, which is catering to a community. There are different healthcare delivery systems. You have employers and business who could be stakeholders even in the healthcare, like the insurance companies. And then you have the media, which is covering all that is happening. And you have the academia, which is doing research. And this is all for the health of the public, right? So there is interdisciplinary effort. It's not an individual, body which does a research and comes up, because all these are stakeholders which help in the development of the policy. Because when you talk of a program, there is involvement of the community for whom you are developing the program. The healthcare system has to deliver this. There is a cost incurred. So whether insurance coverage has to be taken or not, you need media to publicize on this, and then you need academia to do a research and give out that implementation of this has brought about a change or not. So that's a network which has to be there in a public health system. And this is a broad way of looking at it. You have individual behavior, which is accounting for the social, family, and community networks, which in turn determines what is a living condition, and then it goes for the broader socioeconomic, cultural, and environmental conditions. And an interplay of all this is what brings about a change in the health and well-being of the public. So every phase there is evaluation and monitoring, and every evaluation and monitoring there is a need for a statistical component by way of designing the study. So study design, CRD, RBD, everything comes in place, and then you have collection of data which generates data. You have to summarize, present, analyze, and prepare the report. So you have to go for testing of hypothesis. If you have comparisons before the program, what happened, after the program, what happened, you are looking at it. You have a paired kind of a scenario. So you'll go for paired proportions or paired t-test depending on what is your outcome that you are assessing. Okay, so design general surveys. So then you need to decide what is your sampling technique to be used. You have to plan for experiments. If you're planning for any intervention, then you have to show that your intervention is effective. So you have to plan for the experiment. So CRD, RBD, whatever is applicable for that scenario has to be done. And then you have to help the scientists in estimating the extent of the health problem and what are the factors which are determining it. So basically, if you look at the role of a biostatistician in policy setting, you have to first measure the problem, then prioritize the problem, because there are so many problems. What should you take up first? So that is what has to be given, an insight to that has to be given to the policy makers or healthcare providers. Then you quantify the risk association of the risk factors. Now, which risk factor should you target first to control the disease? That again we have to provide. Then you suggest the effect of the policy change, see the cost effectiveness. What is the cost which is going in for implementing a particular policy, and how many of the things are averted? So this is what has to be looked at, right? Same way in the monitoring. So this is looking at the program as a whole, Then you look at the insurance, how much of it is coming in, and you account for both intentional and unintentional biases which could come in. So I'll just take you through this one example before I wind up. So this is a maternal infant health. So what was done was they enhanced the perinatal system. Perinatal system means late pregnancy and early post delivery, right? And this particular county in Michigan had a lot of racism. So they reduced the racism and they fostered the community mobilization. So they identified local people to take care of these pregnant mothers and post delivery, take care of the mother and the child. So with this, what happened was the mortality was brought down. So this was an intervention which they tried and then it was spread out. And that is what we have borrowed by way of our Asha workers and A&Ms in India. And another, as I said, was the smoking. Smoking leads to a lot of cancers, right? Or tobacco use leads to a lot of cancers. So, when I was small, there used to be a lot of advertisement of different brands of cigarettes on the television and in movie theaters when we go to watch the movie. Then in 1970s, the government brought in a regulation in the US to control the or ban the tobacco advertising. So public health campaigns for smoking cessation, stop smoking was started. And stricter enforcement of not to sell tobaccos to children under the age of 18, that was also enforced. Gradually, they brought in ban in smoking, smoking in public places. With this, each of these interventions, they saw a declining trend in cancer. So we are about 2 decades behind them in India in coming in for the tobacco control activity. Okay, so this is another one where vitamin A supplementation was included in the national program. And whether seat belts saves lives. So here testing of hypothesis was done. They looked at with the seat belt, how many of them died, and without the seat belt, how many of them died. And they found an association between that and found that there was an association. But here there are other factors too. Suppose the vehicle in which the driver was going was speeding. Probably the death might be due to speeding and not because of the belt. So then you have to analyze looking at whether, with speed and without speed, what happened. So they looked at it and still found that wearing seat belt was protective. So in this pilot project, they saw this and then it was gradually implemented that wearing of seat belt is mandatory for the driver in a four-wheeler. Okay. Then comes the screening. So this is my last example for application. So screening is for detecting whether you have a disease or not. So we have to have the concept of correctly diagnosing the disease. So people have the disease and your test has to identify them. So we have to have a high chunk which is A and a high chunk which is D, right? So here again we make use of probability and conditional probability. So evaluation of a screening test is done by terms called as sensitivity and specificity. Sensitivity is nothing but the conditional probability. Given that the individual has a disease, what is the probability that the test will turn out to be positive? Specificity is the conditional probability that given that the individual has no disease, probability that the test will result in a negative, right? And further we move on in screening to look at the predictive value of the test. This is nothing but an application of the Bayes theorem that we have in probability. So you apply the Bayes theorem and identify what is the positive predictive. That means I have given my blood sample for testing, I have turned positive. Am I really having the disease? Is what the positive predictive value tells. Similarly, the negative predictive value tells if my test is negative, do I really not have the disease? So these are applications of the Bayes theorem. So I think with this overview of some applications of statistics, I stop for now. And if any of you have questions, you may please address it.
If anybody has questions, ask madam. You can unmute yourself and you can ask. You may unmute yourself and you can ask the question. By the way, madam, your lecture is very wonderful lecture.
Thank you.
And you have explained it in a very nice way. Really, I am very much thankful to you for delivering this session.
Thank you very much. I would like to thank again you and your organization. Thank you.
Madam is very experienced, so you can ask her any question. Yes.
Any questions?
Hopefully.
Yeah.
Hopefully there are no questions.
Yeah,
So
some have asked me for the notes. So have you by any way recorded this meeting? No.
Yes, madam, I have recorded.
You've recorded. So you could please share the recording with the students. Yeah.
Yes. I have recorded it and you will get it. No problem. So if there are no questions, I take chance to thanks madam. So respected Dr. Asha Kamath madam, I am very much thankful for your wonderful lecture. It's a really wonderful lecture in the very innovative topic, public health and what is called as epidemiology. You have very nicely blended the subject statistics and public health and epidemiology. So on behalf of our college, on behalf of our Samstha, on behalf of our principal, vice principal and DBT Star committee from my department, I thanks to you for delivering this good session. I am also thankful to all participants for joining this session. So with this thanks, I think we will take a pause now because at 2 o'clock there is another session from mathematics department. Thank you very much. Thank you very much. Madam,
yes, thank you all. Thank you all and good luck to all the students.
Yes, thank you, madam.